Okay, we're gonna start recording. So what we were talking about last class, which is the last topic of this relatively long learning module, is electrical potential. And remember, we define electrical potential as the energy we require to move positive charge from infinite to a certain point against an electrical field. And remember that we had talked about the analogy of trying to move a rock against a river. And so there's certain energy required to move a charge through an electrical field. And that's what potential is called, or electrical potential. And once we move it to that point, it would be the energy required to maintain the charge at that point in that space. Okay. Now, other things that we mentioned, the electrical potential is a scalar. It's not a vector. Similar to energy, energy isn't a vectorial. It's a scalar, and that means that we're not interested in the direction it's going. We're just interested in the energy that's happening at a certain point. We also mentioned that if we have many charges in space, the positive charges are going to add a positive potential, and the negative charges are going to have a negative potential, meaning that again, if I have a positive charge and I'm moving it against the electrical field, there's going to be a repulsion force, right? So the positive charge is going to be trying to push me away. If I put a negative charge, the negative charge is going to be trying to pull me towards the charge. And so remember the electrical field hockey. You had positive charges that push, negative charges that pull. That's kind of the same thing here. The potential, the positive charges are going to have positive potential. The negative charges are going to have negative potential because they're kind of contributing to that. Okay, so and let's do some problems, some examples here. Oh, and we already mentioned as well that the electrical potential was directly proportional to the charge, so Q, and inversely proportional to the distance. So it's directly proportional to the charge and inversely proportional to the distance. So potential is equal to K, the electrical constant, times the charge divided by the distance to the point that we are analyzing. Okay. This is just a summary of the things that I've mentioned right now. So we're going to be doing 3 problems. Okay. We're going to be doing three problems right now. We have 3 different situations that have to do with potential. And usually with potential, there's 2 ways to look at it. We look at potential at one point, or electrical potential at one point, and we also sometimes are interested in what's called the difference in potential, meaning the difference in energy that exists between one point and another. That's also called the difference of potential. And so let's look at the first example. Whoops. Oh, they're hidden. Give me a moment. Let me just unhide these. 1, 2, 3. Okay. So let's look at problem number 1. Problem number 1. It says calculate the difference between the potential at R equals 5 centimeters and R equals 10 centimeters for a single point charge of 1 coulomb located at the origin. So remember that something that's useful in when we're doing these problems, because they're abstract, is to kind of draw them out. So we have a single point charge, a positive charge. This charge is a 1 coulomb. And we want to analyze the potential at two distances. One, and I'm going to call this one point A, is located at 5 centimeters, at a 5 centimeters distance. And then there's another point B that's 10 centimeters distance. And we want to know the difference in potential in each of those two. Which, assuming that the charge is the same, without having to do any calculations, and this can be a question in the exam, which of the 2 points would have the highest potential? Okay, because it's closer, correct. Because again, we're working against the electrical forces. So if I have a positive charge and I grab another positive charge, the closer it is, the harder it is for me to maintain it there because of the repulsion forces. The farther it is, the electrical field is weaker, and so I would need less energy. So correct, it is A where we would have the larger potential. So let's calculate each of those. So we're going to calculate the potential in A is going to be KQ, which is the charge, divided by the distance in A. And so we know that K is the electrical constant. That is, I had done this setup so I wouldn't be facing completely backwards to the people that were online, and now I'm facing backwards to everybody over here, but it would be the same thing if I'm writing on the whiteboard, so whatever. So here in the classroom, you can read the writing, right?
Yeah.
It's better than the whiteboard.
I don't like to write in the whiteboard, actually.
Oh, no, I'm telling you that it's better actually than in the whiteboard.
Oh, no,
Because,
yeah.
Like reflective.
Yeah, no, but what I mean is that I'm actually doing this because I don't like to write on the whiteboard. Somehow my writing gets even worse when it's a larger space, and at least it's a little bit more controlled here. And the other thing, I don't know if it happens to you guys, but I really don't like the smell of the. If you like the smell of the markers, then you have a problem. But I don't like the smell of the markers, and you have to literally erase. If you don't have the eraser, I'm more given to erase with my hand, and I end up with my hands all filled with muck, and so that's not fun. 9 times 10 to the 9 newtons. Newtons meters squared coulomb squared multiplied by the charge, which would be 1 coulomb, and the distance of A would be 5 centimeters, which would be 0.05 meters. Remember, for the potential, it isn't squared. It's literally the distance.
I have it, but I don't know if it's for.
Oh.
She's a friend.
So it's the technique. Let's see. I have the answers on the other side.
1.8 times 10 to the 11.
I think that's correct. 1.8 times 10 to the 11, and these would be, what units are we using here? We use volts, correct, volts. Or joules divided by coulomb. Joules divided by coulomb, which is energy by unit charge, or volts. So these would be volts. And please, everybody else verify the. Perfect, good job. Then it's going to be KQ divided by RB. This would be 9 times 10 to the 9 newtons meters squared coulomb squared by 1 coulomb divided by 10 centimeters, which would be 0.1 meters.
9 times 10 to the 10.
9 times 10 to the 10?
Yes, and the V. What is the V? Volts.
Volts, voltage, volts. And what we're being asked to calculate is what the difference in potential is. So what is the difference in energy between one point and the other? So we're going to say that the AB would be VA minus VB, which would be 1.8 times 10 to the 11 volts minus 9 times 10 to the 9 volts. And so the difference in potential, which would be the 10, yep, yep, yep. Correct.
It's half.
Would be half exactly because of the relationship that we have between the 10 centimeters and which would be 9 times 10 to the 10, right? And that would kind of be a measure. This difference that we calculate would be kind of a measure as to how much energy I would need to move from A to B. Or from B to A, depending on the direction that we're looking at. And once we later on, much later on, well, later on in this course, which is unit 3, that has to do with electrical circuits, but even deeper on in next semester in the industrial electronics course, we're going to be talking a lot about voltage. And voltage is also called a difference in potential. And the difference in potential is usually because we're looking at the movement of electrical charges from one point to the other. And so that's why we're interested in the difference in energy that's required to going from one place to the other. And that's basically what's called the difference in potential, or the voltage that we usually work with. Usually we're used to working. I'm going to take a screenshot of this and give it a few seconds so you can copy. Remember that all of this is added to the PowerPoint. So I'm going to be recording. I don't know how the audio is going to be. I don't know how when I move, if its computer is catching it. So this is kind of an experiment. But remember that the recordings from last year are all there from 2021. So you can access those as well. Okay, question with this one. It's a relatively easy example, just explaining the concept of the difference of potential or electrical potential. Okay, any questions with this one? No, we're good. Okay, I'm gonna clear and jump to the next one. Okay. Now, sure. Let's look at another situation, and this is basically just like these mental push-ups that you guys are going to be doing, because the homework tasks that you're going to do are going to be different situations with different geometrical figures. So you're going to have to practice your math and your geometry. So right now we're going to be working with a triangle. Let's assume that we have a triangle. We've got 3 charges of the values that are indicated there. It's an equilateral triangle. Each side is 1 meter. And we would like to find the electrical potential at the center. So assuming that we have a triangle of charges, and again, we want to move a charge to the center from infinity to the center of the triangle and maintain that charge there, how much energy would we need? So let's do some drawings here. We've got an equilateral triangle. I have done this joke with you guys, right?
Which one?
This one.
No.
No.
It's a
Yes.
Patrick.
No, I did. I have done this joke.
Yes, I know.
Yeah, it's the Bermuda Triangle. Yeah.
So what?
It's a Bermuda Triangle.
It looks like
It's the-
Patrick from SpongeBob.
Everybody at the first try thinks about Patrick. It's the worst. It's the worst drawn joke in history. Sort of combination. I wasn't looking at you guys, but I love the laughs. The laughs were really sincere because I said Bermuda Triangle and I just heard, oh. Extremely funny, Professor. Please take note that I have laughed at your joke. I always put forth that my jokes are terrible. My daughter hates my jokes because she said, you're not gonna do this. I do dad jokes. I do dad jokes. Terrible dad jokes. So we've got an equilateral triangle. Each side is 1 meter. And we've got 3 charges on each side. I'm going to place them like this. We've got a positive charge here of 1 column. I'm going to say we've got another charge here of 2 columns, and I'm going to say I've got another charge here of 3 columns. Trick question for what we're going to be doing. Right now, we're talking about electrical potential or energy. Remember, think about this. It's the energy I would require to grab a charge and put it here in the center. Okay, that's what we're talking about. Okay. And so, does it matter in which order I put the charges in the track? They're all the same distance in the end. So it doesn't matter if I put the 1 charge here. It doesn't matter the order because in the end, all of them are contributing to a certain energy ratio. Okay. So it doesn't really matter the order.
So like we're searching for energy that is going to.
Yes, that's a way of interpreting it. So what we're doing is that we're placing ourselves here in the center of the triangle. We're placing ourselves here in the center of the triangle. So assuming that I would grab a positive charge and put it in the center of the triangle, how much energy would I need to do that? And again, imagine that there are forces there. So literally imagine that there are forces in the triangle. And you're trying to put something there that's going against those forces. How much energy would you need there in that point? And that energy would be different if it's inside the triangle, if it's outside, if it's further away, if it's closer, because of the way the electrical fields behave. So right now we're there in the center. So we're gonna, I'm actually going to give you guys a couple of minutes to think about that. I'm gonna give you a couple of minutes to think about it, and then we're gonna solve it here.
Of what we need to do.
So we need to calculate here the electrical potential, but we need to find some distances and some stuff there. So I'm gonna give you a couple of minutes to try to see what you're gonna do. Remembering that electrical potential is going to be K multiplied by the charge divided by the distance.
We're going to use the Pythagoras, like divide the triangle in 2.
We're going to have to do some triangles there, maybe find some angles. Yep.
Is there any way we use the formula of the multiple point charges, or we have to do it like separately?
Oh, okay. So for all these situations where you have more than 1 charge, you calculate the potential separately for each one because each one is contributing. And then the multiple point charges, you're going to algebraically add them.
Oh, okay.
And that's it's important that it's algebraic because it's a scalar. So we were not looking at vectors or anything like that. The positive charges are positive, the negative charges are negative, and you just add them up.
Okay. Because it's so first we're going to find the distance.
We need to find the distance. Yep, correct.
But it's not one. Is that it? No, but that one seems very.
No, because what we're looking at, let's number these charges just for the purpose of, let's call this charge 1. Let's say that this one over here is charge 2. Columns, and let's say that this one over here is charge 3. And so we're looking at the center of the triangle, so we need to find these distances.
To find the electrical first, the big one.
Exactly. So we've got these 3 distances, which are actually the same. I'm going to call this R. I'm going to say this is RA. I'm going to say they're actually the same value.
So just calculate one and we can.
Yeah, exactly.
Because something's right here.
It's the same R2 and R3, but actually R1 is the same as R2 is the same as R3, and we need to calculate that. We need to calculate that distance.
Do you have to do the right triangle in order to solve it? Yeah.
So let's look at this here. I'm going to create a right triangle here. Boom, I'm going to create a right triangle here. I'm going to zoom this over here. And that right triangle that I've just created, this distance here is R1. Let's say it that way. We're going to say that all of these are the same and they are equal to R. That way we don't have to use the. And what other information do I have in that right triangle that I just created? The angle, what would the angle be? Well, this angle would be 90, correct? But
45 and 45.
no.
No, 60, 30.
Oh, yes.
Okay, so if the triangle is equilateral, all of the angles have to be 60 degrees inside. So this angle here, this complete angle is, I'm going to call this one, but this whole angle is going to be 60 degrees. So this angle here would be 30 degrees. And so this angle here is 30 degrees. What other information do I have? I'm trying.
You divide the 1 into 0.5.
Correct. The distance here on the bottom, it's exactly divided in half, so this would be 0.5.
And also the height.
We know the height. Would that be 0.5 exactly?
Yes.
Maybe I'm going to say it this way. Maybe it is, maybe it isn't. I'm not completely sure. But with that information that we have there, we can calculate R. How can we calculate R? Well, we use some.
Professor, and we can do it like divided the angle in half and then.
Yeah, that's another way of doing it. You can divide it in half.
Like.
Oh, yeah.
Difficult. Yeah, it can be.
You could also do it that way.
And the
Yeah.
answer is divided by two. Because it's in the middle.
I'm not, is it exactly in the middle from each? It should be in the middle. Yeah. We should get to the same value. Let's do it both those ways. And let's verify. So here, we would have that the cosine of the cosine of 30 degrees should be 0.5 divided by R, that would mean that R is equal to 0.5 divided by the cosine of 30 degrees. Can somebody give me this value, please?
0.57.
0.57. Let's leave it at 2 decimals. You guys can use the whole decimals. Let's use 0.57. And so now, what we need is to calculate the electrical potential for each of these situations. So we're going to calculate them separately. So the potential for charge 1 is going to be K Q1 divided by R, which is going to be 9 times 10 to the 9 newtons meters squared coulomb squared, multiplied by 1 coulomb divided by the 0.57. I'm going to be writing down the expressions, so please do those calculations when you have them. Then the potential of 2 is going to be K Q2 divided by R, which would be 9 times 10 to the 9 newtons meters squared coulomb squared, multiplied by 2, which is actually going to be 2 times the first one. But let's leave it, it's going to be like, let's leave it at 2 decimals just to round it out. It's 1.57 times 10 to the 10, and these would be both. Are you sure, Lisa?
I got this.
Good. And we've got V2 here. And then let's see, V3 would be K V3 divided by R. So give me the other 2.
I got 3.12 times 10 to the 10.
That should be the double of this, 3 point. And the third one.
Or 0.73 times 10 to the 10.
So remember to verify these calculations, the rest of you. Yes. Yep.
So why isn't the Q2, shouldn't the distance from the center be different to the height?
Well, if we do, it should be the same, because if we do the same analysis, so we did the analysis for this triangle here, but since it's an equilateral triangle, if I were to flip it, it would be it should be exactly the same. Because my triangle doesn't look like equilateral, because if it were an isosceles, then the distance should be different. And so once we have these 3 values, the total potential here in the center, I'm going to call it VT, the total potential is going to be simply the algebraic addition of the other potential. So since all of the charges are positive, all of the potentials are positive as well. V1 times V2 plus V3. And so the total would be the addition of these here. So can somebody give me that value?
I got 9.44 times 10 to the 10.
No, it's 2, that's- Let's verify that one, please.
Yes, I got the same.
So that would be a measure of the energy per unit column required to have a charge in that center point. To have a charge in that center point according to this distribution. Now, again, just to try to understand this, so what we're looking at is we're looking at a situation where we have charges in space. These charges particularly make up a triangle. And so if I were to bring a positive charge from infinite to that point in the middle of the triangle, that's the energy per unit column I would need to maintain it there. Now, a question that doesn't have to do with calculations. If I were to change one of those three charges, and instead of that charge being positive, that charge being negative, any charge, any of the charges, would I require more or less energy to maintain it there?
Less energy.
I would require less energy because that's the next example. Mathematically, the negative charges subtract. But also, in reality, the positive, I'm bringing I'm in infinity. And I'm a positive charge and I'm going towards the triangle. Those three positive charges are generating an electrical field that's pushing me back. So I'm trying to go against that. And I place myself here in the middle. So that's this energy that I require here. There are three charges that are pushing me back. But if I change one of those charges to a negative charge, suddenly there's going to be two charges pushing me back, and there's going to be one charge attracting me. Okay? So I'm going to, in theory, I should need less energy to be able to move to that point. Okay? That's the next situation that we're going to be talking about. Let me take a screenshot, let you guys write this down. And see if you guys have any questions. I hate face masks.
Professor, I still can't understand why charge 2 has the same distance if the height should be higher than the 1 meter, right?
Well, the thing is, let me draw this here. Okay, so I already took a screenshot. Can I erase the rest of it? Is it okay? Erase this. Okay, so, and it's to clear, it is important to clear it up. So, we're talking about three distances, right?
It's good. I did,
Pythagoras.
I did Pythagoras and I did the 1 meter square equals 0.5 square plus u square, something like that.
Uh-huh.
Yeah, so I got B, which is the height from the middle of the bottom to the charge 2.
Okay, you did Pythagoras with,
The 1 meter and 0.5.
Half of the.
and that would be half, and that would be half of that to get to this point, right? And you got a different value?
You got different value. Yeah, you get point.
We're not getting the distance from the corner to the center, we're getting the distance of the
From the middle to the.
From the middle to the center.
We
It's a
talking
different
about
name.
the-
Oh.
From the bottom middle.
That's why.
Yeah. Uh-huh.
Because like the center of
I
the
had
triangle,
someone.
Uh-huh.
but it's not the same number as from the corner to the middle.
He's not using the R, he's using the other one.
Ah,
Ajá, the one of the 90 degree.
So,
Ajá,
You're using
that's
this
why
one?
that one, we need the one of the corners to the center.
We need, this one. Let's see where you're getting a different value, because if we analyze, so this triangle here that we zoomed in here, was this, just before we go, is this part clear when we zoomed in on this triangle?
I got that.
The two bottom ones are.
Professor, but it's because I don't want
Can we do the
to.
other?
And so this one, what I'm saying is that if we grab this one here, oh, so what you're saying is that this one, this point here wouldn't necessarily be the middle point?
No, I think probably, yes, because what they're saying is that they did, like, Pythagoras calculating to calculate the center line of the whole triangle, and then they divided it in two, but
But that
both
wasn't,
sides-
I don't think that would necessarily be the center of the triangle.
Yes,
Would it?
that's what I'm telling Andrea.
So that's, so what you're saying is that, so you did this here.
Yes.
Yes.
That, so
Okay.
I divided the whole triangle in two.
Uh-huh.
Instead of just dividing it from the center. and-
So this would be 1 meter, this would be 0.5 meters, and then you got a value here.
Yes, and then that value I divided it by two, and that's like.
But why it's not the same number?
But I think it's because it's not, like, it's the center of the triangle, but the line is not necessarily divided in the middle.
So this would be here, and you got a different value from this side to this side here. And we got, what is the value you got here?
I just got the whole value and then divided by
What is the whole value?
0.866.
0.866 is the whole value. Okay, and we got that the center, we got 0.57,
Yeah.
Okay. which would be a little bit lower than this one, if you think about the middle, right? Okay. Huh. Okay, so the question here is, which would be the center point of the triangle? Huh? Because if it's an equilateral triangle, it does make sense if we're putting half of it here, this would be our, this would be the distance here, and the distances should be the same. The distances should be the same for the three of them, okay?
I think I already know what the problem is, but I'm not sure.
No, but you, no, but it's fine, because you kind of got me thinking, because the distances should be the same.
Professor, but it's because I don't know if I can name it. Like, for example, you have the triangle and not, this is the center, for example.
Yes.
This is the center and not necessarily this distance will be the same as this one. Like, if you do the 3 triangles,
Mhm,
this distance would be the same as this, not this, you know?
mhm.
I don't know if it makes sense.
Yes, because of the proportion.
For example, the top part should be equal to the diagonals, not the bottom half.
Because the little ones are not equilateral triangles.
Yes.
Mhm. So the calculation is correct when you're doing the Pythagoras, but what I believe is happening is that the center of the triangle isn't necessarily at the center of the line that divides it in the middle, because of the proportions. Okay, so it's like, what Jason was mentioning, so we have this distance here, and then we have this distance here. This distance is gonna be the same as this distance. Okay, these two are gonna be the same, and this one is gonna be the same, and the other three are going to be different as well, to calculate the center of the triangle, okay? I think that's what's happening, because if we do the right triangle here, okay, this would give us this, this middle point that's dividing the triangle in half, okay? And so in this sense, R1, R2, and R3 are the same, and these other distances here that I'm gonna call X, Y, and Z would be the same amongst themselves, and the addition of those would be the complete line. Does that make sense?
No, I understand, it's just a question for if someone didn't.
Yeah.
Is the point that
Why is it no? Yeah. But is it clear then to everybody? It was a good question, because we do have to kind of have to think about that, because we could have assumed some other things and not necessarily be mathematically correct. Okay, so it is clear then? Okay, good. Yeah, triangles make people. Okay. We're gonna do the next one, and in the next one, I don't wanna eliminate all of the drawings, because we're actually gonna need some of them, so we don't have to repeat them. For the next problem, we're actually gonna be using, we can use the same values that we have. I'm gonna erase some of the things here. Yes. Now, the difference between this situation. The difference between this situation is that now Q2 is going to be minus 2 columns. Actually, the calculations are going to be the same. The calculations, the three values are going to be the same. The only difference is that now we are considering the signs. So in this case, V1 is still going to be the same calculation. I think it's what, 1.57 times 10 to the 10 or something like that.
Yes.
Columns. V2,
It's just gonna be negative.
it's going to be the same, but it's going to be negative, and I think this was 3 point what?
12.
12. Huh?
I wrote down 12.
And V3 is going to be the same value, but it's going to be positive, and this was 4.73 times 10 to the 10 columns. And so the total potential now is going to be algebraically V1 plus V2 plus V3. But now V2 is going to be negative. So we're going to have this one plus this one, but we've got a negative sign here and plus this one here. So that value should be smaller than the one we did on the last one.
Almost done.
Well, because I calculate that we took using 3.15.
15, we can do it.
Yeah.
3.18.
Say 3.18.
So it's a little bit less. Because the negative charge is
I think
contributing.
because we rounded up, that's why it's like such different.
Let's do this for exams and exercises from now on, the homework tasks. Let's use 2 decimals. Okay, let's use 2 decimals. Or rather, if you're gonna be cutting off decimals, then use 2 decimals. If you use all of the decimals in the calculations, that's fine as well, if you can keep them in your calculator.
So we just use the tenths and the hundredths.
If you're going to be using all of them, it's fine. Again, if I were to be grading this and some of you got 3.18, some of you got 3.15, or there's a small variation here. It's not wrong. And again, it is because of the decimals, because again, we're working with either very small values or very large values, and they're going to be sensitive to that. Okay. Save this.
Professor, showing this operation is still the sign of the charge.
Yes, it is important. That's a very good question, Anya. When we were working with forces and electrical fields, the signs of the charges are used to identify the direction of the vectors. Here, with potential energy, since it's a scalar, positive charges contribute positive energy, negative charges take away energy. So that's literally, we use the signs of the charges are directly going to be influencing that. Okay. Questions with this one before we?
No.
Okay, so with this topic, actually, we're closing up learning module number 1. Okay, so a few things having to do with housekeeping. First off, there is a homework test. So it's homework test number 3, I think, which are some exercises of the whole unit, of the whole learning module that cover all of the topics. There's not many exercises. I think there's just 3 sections. Those are already in Blackboard. Those are due by Friday before midnight. Okay, Friday before midnight. The solutions to these are going to be posted next week. So you can have them and check them. Okay. Those are individual. Okay. And you can start working on those and asking questions. We are going to be doing the exam. Let's do the exam next. The other Monday, it's no, the other Monday.
No, the other Monday is good.
It's-
We're good.
No, it's
Next Monday.
no, it's holiday. 21st. Not this Monday, the other one.
No, it's here.
But I think it's on the.
When do we have spring break?
Oh, no, it's on the 11th. From the 11th to the 15th of
That's
April.
spring break.
11th to the 15th.
The spring break.
Professor.
That's what I have here on my calendar.
April,
Excuse me? April 11th?
Only Monday.
Monday. Well, actually, it would start on April 9th. But yeah, that's what I have here on my calendar.
And since we're on break, we're gonna have to take that off.
The exam. No, we're not gonna make the exam until April. No. So. Yeah, it's fine. Let's have the exam. So the homework test, this homework test, which is the important one because you're gonna be reviewing exercises for this Friday. Okay. And
We should review on Monday and have the exam Wednesday.
no, we don't. Well, we could. I was gonna suggest we have it on Friday, the 18th.
Oh, okay.
Yeah, it's okay.
Would that be okay?
Yes, perfect.
Friday, the 18th. Now, important. The way we're working here in the class is that we have the learning modules or units. So this exam is going to cover only the material of learning module number 1. And in Blackboard, you can clearly see what that is. We're going to start, and with what you did last Friday is learning module number 2. That's a different topic, which has to do with capacitance. That is not going to be covered. By the way, something that we haven't talked about, and I wanted to wait to see what was going to happen with us coming back and all that, is that we are going to be doing some lab work related to the course. We're going to be doing some exercises for each unit. The way we did it last year is that for unit 1, what we did were a series of exercises or experiments that actually, because we were online, there were experiments that you could do at home, actually with stuff that you could have at home. So what I think we're going to be doing for the lab exercises of learning module 1 is that I'm going to let you know probably in a couple of weeks We're gonna have a session. I need to see what the lab situations are. I don't know if everybody can fit in the lab at the same time. I need to ask about that. And basically what I'm gonna ask you to do is to bring some stuff here, and we're gonna be doing some experiments that have to do with electrostatics. You can actually Google them. It's a typical experiment where it seems like magic, where you're moving things around with electricity. We're gonna be doing some experiments in the lab. That's gonna be for learning module 1. And so in each learning module, we're gonna have a lab exercise that kind of rounds out stuff. And that's gonna be for learning module 1, but I'll let you know when we're going to be doing that. Okay. Okay, let me save this. This updated PowerPoint is gonna be available later today. Okay.
O sea, el domingo llegó el tipo,
Okay. Okay, everybody. So we're going to start off. Yes. We're going to start off learning module. We're going to start off learning module number 2. So this is not going to be covered in the exam. This is a much quicker learning module than the first one. The first one has a lot of stuff in it. This one is much shorter, and I think much simpler as well. So learning module 2 has to do with capacity. And I asked you guys to do some research with regards to capacitance on Friday, just to kind of introduce the topic, capacitance, capacitors, etc. And we're going to be talking about that, and you can comment on what you researched, and we're going to be talking about that. So we're going to be remembering the God of Thunder. From now on, this is kind of a preview of stuff that we're going to be seeing more in detail in the industrial electronics course next year, next semester. I said we. I don't know if I'm going to be teaching that course to you guys. I hope so, but basically this course has a lot of the theory. The industrial electronics course is the more direct applications of things that have to do with electrical circuits and electronics. And so from now on, we're going to be seeing certain things that are properties, okay? And certain values like capacitance. And then we're going to see that the device or the thing that represents capacitance is going to be called a capacitor. And then in the next unit, we're going to be seeing a concept called resistance. And the object that is used in electrical circuits that has a resistance is called a resistor. So one is going to be the concept and the other is going to be the physical thing. And so we're going to be doing the analogy here with Thor. So capacitor, this thing that Thor has in his hands, that's the symbol of a capacitor. It's very simple. What does that look like? The symbol that, what does that look like?
It looks like a stick with an Oreo.
It looks like a stick. That's actually, Ricardo, that's a very good way of looking at it. Because I was gonna give a different example, but the Oreo example is gonna be even better. A capacitor is an Oreo cookie.
Oh, because it's two metal plates and there's like the filling of the.
Exactly. A capacitor and capacitance, just to remember that, I was gonna say, I always make the analogy of a sandwich because you can create different things with a sandwich. Well, it's an Oreo cookie. And you know that there's different types of Oreo cookies. I don't know why they've done this, but there's the one, some with the white one, the lemon one, etc. Oh, there's one that are thicker that has.
There's one that's just nothing but stuff.
Mhm. There's other ones that are the smaller, but it's an Oreo cookie. And what is an Oreo cookie? It's two pieces of cookie. And in the middle, there's something that's filling those in. That's basically what a capacitor is. And by the way, I'm not oversimplifying things. That is literally what a capacitor is. It's two conductive materials with another material in the middle, creating a sort of sandwich or Oreo. But that basic configuration electrically generates a lot of use or a lot of applications. So how are we going to remember things in this unit? We're going to be talking about capacitance. And if you think about capacitance and the word, it's kind of like talking about capacity. Okay, so capacity or capacitance or a capacitor is something that is going to be able to store electrical energy. Okay, it's like it's something that can store electrical energy. And it's basically going to be an Oreo cookie. That configuration of the Oreo cookie is going to give us, and I don't know if other professors have done this recently, but I'm going to do it because I did it when I studied this course, and I thought it was a very interesting exercise. The lab practice of unit 2, and since we're back here, we are going to be able to do it, and I think that's actually going to be a little bit fun, is that you guys are going to create a capacitor. Okay, and that it's literally very simple. I can create a capacitor just grabbing two things, and there's a few configurations there, Juanignacio, that can create larger or smaller capacitance, etc. But I can create a capacitor just making an Oreo computer sandwich. So what we're going to be doing is this. The lab exercise of learning module 2 is that you're going to create a capacitor. But you're going to have to demonstrate with calculations that the capacitance that you're measuring is according to the calculations. And actually the formula of a capacitor is a very simple formula. And we're going to do a bit of a competition for bonus points. Whoever has the largest capacitance is going to get some bonus points. And there's many ways to do that. There's many creative ways to do that. Okay. That have to do with some things that we're going to be mentioning. I'm going to let you know when we're going to be doing that eventually, but that's going to be the lab exercise for learning module 2. And so a capacitor is going to be a component or an electrical component that has the capacity, and just remember that word capacity, to store electrical energy. In the form of a static electrical charge. So it's kind of like a battery. It's kind of like a capacitor is kind of like a battery. It can store electrical energy within itself. And well, imagine if I can have a small device that stores energy, that can be very useful in electrical circuits. I think I don't remember if I mentioned this example to you guys before, but remember when you have electrical devices, any sort of electrical device, that they usually have warnings on them. And the warnings say that do not, if you're not an experienced electrician or a don't service them, don't open them up and start working them. And a very dangerous misconception is that if my electrical device is disconnected, it means that there's no electrical energy. And that's a very dangerous misconception. Why? Because within my electrical device, we have capacitors. So a capacitor, imagine that it's this thing that stores energy. It's like having a tank, because actually physically some of them look like tanks, like little tanks. And you're storing energy there, like if you were storing water in a tank, okay? And to store water in that tank, you connected it to a hose. And the tank filled up, and then you disconnected the hose. The tank is still filled up. Okay, so if the tank breaks, you're gonna get wet. The same thing happens with an electrical circuit. Inside an electrical circuit, there are capacitors. These capacitors get charged up when the circuit is connected. Once we disconnect the electrical energy, the energy that stores doesn't dissipate instantly. It takes time to dissipate. So you might have a device that's connected, it's working, it's storing energy in its capacitors, then you disconnect it and you're assuming that there's no more electrical energy in it. However, the capacitors have the energy stored. So if you start working on it and suddenly touch something, the capacitor is going to discharge on you. So that's why servicing electrical equipment, even though it's disconnected, could be dangerous because of the source. Yes.
For example, if I'm cleaning an electrical device, like an appliance, like something in the kitchen.
On the outside.
Yeah.
Meaning it's not open, you can't see the circuits or anything like that.
Yes.
Yeah,
exactly.
that's what I mean, right? An electrical, when I say servicing, it's like you've got your microwave oven and you disconnect it and suddenly you say, I'm gonna open the panel and I'm gonna start working on the circuits inside. That could be dangerous.
But if, for example, I wash some potentially with water and.
Let's say that a friend of yours washed something that shouldn't have been washed
Like
electrically.
a waffle maker.
No, that could be,
Can it be damaged?
yes, it could, depending on how well, no, depending on how well sealed it is. Yeah. No, no, how does a, if I'm thinking about a simple, I'm not, for those examples, because there can be these smart kitchens that have these devices that are really intelligent. No, it's a waffle maker. It's a normal waffle maker.
Yes.
Right? Okay, so how does a waffle maker work really internally? Next, the next learning module that has to do with resistance, we're going to be talking about that every material has a resistance to electrical energy. Okay. But remember, there's a basic principle here. Remember, electrical energy or electrical current is movement of electrons, and movement generates heat. And the opposition to movement can generate heat. So a waffle iron, a toaster, or whatever, they usually have inside of them a piece of metal. And that piece of metal, you're putting electrical current on it, and that has a certain resistance. And because of that combination, it's getting heated up. Okay. So
it will not get damaged.
Well, depends. If it's well sealed, one is the piece of metal. If that gets wet, the only thing that's going to happen is that probably when you turn it on and it gets heated up, there's going to be vapor coming out.
Okay.
That's the metal part. It's like if you turned on your stove and had the metal rings or whatever you're sewing, you throw water on it, there's going to be steam coming up. That would probably be one thing. But that piece of metal is connected electrically to the socket. If that part isn't completely sealed and water falls there and you connect it, you could create a short circuit. Okay. So either of those situations could occur. It depends on how well sealed it is. So the question I would ask you for your friend is, you cleaned it, because I mean, there shouldn't be a problem because appliances in the kitchen, it's expected that you will be able to clean them. However, if you notice, most electrical appliances in the kitchen have these indications to clean them with a damp cloth, not a wet cloth. Okay, so if you when did your friend do this cleaning?
In the morning.
Today?
Yes.
Okay, what I would suggest in those situations, leave it in a place where the sun can hit it, or somewhere really dry, and wait for a long time for it to dry, because it should dry. Um,
How do I know the capacitor has been
Okay, so let's listen. So Ricardo says, how do I know if the capacitor has energy in it? You would have to literally measure it. It's not a device where if you look at it, you're gonna be able to.
it's glowing or
No, actually, no, that's actually, that's actually a good question. And that's why it's important because in the servicing of the electrical equipment, there isn't gonna be things in the electrical board that are gonna tell you. So the capacitors are gonna be there. You're not gonna know if they're charged or not. There's not gonna be something visual that you're gonna know. You would need to literally measure.
Like the capacitor, can it be like the one, when you measure that wants to know what's the volt?
Yeah, it's basically the same device.
The same one?
Yeah, the device that we use, the multimeter, we just need to find in the multimeter this symbol. What Estrella is talking about, there's these devices in electronics called multimeters. It's literally multimeter. It's a device that is used to measure different things. And so basically, they're usually used to measure voltage or current, but they're gonna have settings where there's gonna be these different symbols that we're gonna see during the course. And if it has a capacitor symbol, you're gonna be able to measure the
It's
capacity.
because my dad has it, and he demonstrated me like how to measure it.
How to measure that, there's polarity. So if you have one of those, it's gonna, the lab exercise of doing the capacitor is gonna be even easier because you can measure it at home. You don't have to measure it here. So yeah, so that's important with regards to electrical charges. And let's hope that the waffle maker can, of your friend can works out well. And so a capacitor in its most basic form, it's this sort of sandwich. Okay, it's a sticker. Yeah, it looked like something very, very different from over here. And even if you're doing it with the, yeah, it looked like dust.
No.
It looked like white dust.
It was very ugly.
Yeah. Can I give you what is usually called a mother's or grandmother's tip to removing stickers? Yeah, it literally works. If any of you have stickers that you want that you remove and they something less damaging with peanut butter.
With
Just-
peanut butter.
I swear on this
Peanut butter.
because I put a lot of stickers on stuff, and when I buy DVDs or whatever, the stickers, and I like them to be clean, just grab a little plain peanut butter and put it on top. Wait for, I don't know, less than a minute, and then just grab a cloth and wipe it. It will completely come off without anything.
So you can try with a blow dryer. You just wait till the glue has like melted and you just lift.
That could also, just that, for example, that's why I mentioned less damaging, because if it's a computer, you might not want to have the blow dryer.
I
that-
know, it's the iron.
Yeah. Because of heat. So peanut butter. So a capacitor is basically going to be like the Oreo. It's going to be the two conductive plates. That's the important part. The chocolate cookies of the Oreo, in this case, are going to be conductive materials. They're usually metal plates or some sort of conductive material. And in the middle, there is going to be a material that's called a dielectric material. It's going to be a material that has a certain insulation. Depending on the type of material that we put in the middle, we're going to have different values of capacitance. And notice that these images there, those are images of typical capacitors. There's many types of capacitors, but this is an image of a typical capacitor. And do you notice that it's a cylinder? It's kind of like a cylinder.
Yes.
So that's why I mentioned that the capacitor, imagine like when you're thinking about electricity, think about the analogy with fluids. So imagine that literally the capacitor is a tank. Okay, it's a tank that stores energy, and they kind of even look like tanks when you see them in circuits. Now, there's a reason why it's cylindrical. And it's actually a geometric configuration reason. So I just said that in a very basic capacity, the capacitor is kind of like an Oreo. I'm gonna switch over to talk about sandwiches because of the following. I want you to think right now as a square, not a circle. The same principle applies to a circle, but I want you guys to think about a square. Think about a sandwich. You're creating a sandwich. And so the sandwich is basically the two pieces of bread and there's something in the middle. Let's say that you are really, really hungry because all of you are really, really hungry right now, like myself. And so you want a sandwich that satisfies your needs, right? Would everybody agree that the larger the bread, the larger the sandwich is, and the more stuff I can put in? Right? We're okay up to that point. So let's say that I have a sandwich that's about this size. Okay. Let's see the offensive line over there. You guys are big guys. You need sustenance. Would a sandwich of this size with just like maybe some ham and cheese would be enough for you guys? No, it wouldn't. Right? So we'd like a larger sandwich, right? What happens if I tell you I'm going to give you guys each of you a sandwich that's the size of the table? Would you guys think that would be enough for you guys? A sandwich the size of the table?
For Javier,
No, for each of you. For each of you. Could be yes. But would it be really practical to have a sandwich the size of the table? It's impractical for you guys to even grab it, right? Is that clear? We could cut it up, but then if we were to cut it up, we would have many little sandwiches instead of having one big sandwich. Is there a way of making this very large sandwich that's the size of the table? Is there a way of making it smaller? Well, but we can, no, you're making a bigger sandwich. So I can, if I start making it tall, it's still this size. So I have to do this to pick up the sandwich.
we can cut it.
But if you cut it but without generating more, so cutting it would mean making more sandwiches. It's the same sandwich, but I want to make it smaller because I want to fit it into my.
You can hold it.
We can fold it. We can fold it. That's so instead of having it this size, I can fold it and I just made it half of its size. And then I can fold it again and again and folding it. And that's basically the concept of these like sort of gyros and wraps. We can roll it. So instead of folding it, we could roll it. And notice that the amount of area that I'm covering if the sandwich is flat compared to the amount of area that I'm covering if it's rolled up, the rolled up sandwich is much smaller. And I can make if I roll it up really, really tight, I can have something very large that's reduced in area. Well, that's why capacitors are cylindrical.
To maintain that energy.
If I open this up, this is actually a wrap. It's very, very, actually, when I was in school, we used to, well, yeah, it's being recorded. We used to blow those up in the lab. And when you blow them up, it's kind of like a party favorite. So because it's wrapped up, when you blow them up, they kind of go, they twirl because it's two strips of metal that are very large with something in the middle that somebody rolled up. And that way, the surface area that was very, very large, I could compact it and make it into something much smaller. So that's why a lot of capacitors are cylindrical. It's basically this roll up that's being done of. So that's a tip for your lab exercise for this unit. You could create a capacitor that's rolled up. But when we roll it up, we have to be very careful of how the bread is touching each other, because that can generate problems.
Are we gonna make capacitors out of food?
No, they wouldn't work. But it's a fruit roll up with Oreos in it. Exactly. Okay. So basically what's happening here is that we're gonna have the two plaques or plates. We're gonna have the material in the middle. That's gonna be the dielectric. It's called the dielectric material. And the symbol is gonna be like that. It's gonna be like the Oreo cookie. By the way, there's a variation on that symbol. We're not going to be needing that variation right now in this course. I'm just mentioning it because in the industrial electronics course, it might be relevant. There's a variation with regards to this symbol where the capacitor symbol looks something like this. Instead of one of the plaques being straight, the other is curved. The only difference there is that a capacitor, once we charge it, automatically takes a polarity. So there's one side that's positive and the other side is going to be negative. In this symbol here, when a capacitor has this symbol, it means we don't care which one is positive or which one is negative. When the capacitor has this symbol, it means that this is positive and this is negative. And actually in the drawing, in the image that I showed before, I think we can, let me see if we can see that. Yeah, actually in this image here, notice that there is an arrow here with a little rectangle in the middle. This rectangle in the middle means negative. It means that this little leg here is the negative one and this one is the positive one. So sometimes the symbol is going to be modified to this one. In this course, actually, we're not going to be really caring for that, but it is a variation that we can have. Okay, questions up to this point?
No.
Okay.
Which way is the current flow, from negative to positive?
It would go from negative. Well, actually, it goes when we see electrical circuits. It's actually we're going to be considering that it goes from positive to negative. It's going to go from the place that has more potential to the place that has less potential. Right from now on, because we just finished up talking about electrical potential. Notice that this is voltage. This is a power supply. So the positive and negative when we're talking about voltage is positive potential and negative potential. And so usually we go from where there's positive potential to where there's negative potential. Or the part that has more energy is pushing the electrical charge towards the part that has less energy. Okay, so we're gonna break here. I'll see you guys on Wednesday, and remember start working on your homework task 3, okay? For Friday before midnight. Yes, before midnight.